Today everybody, we would like to present our Physics Task 1 investigation on question 4, that is wireless power transfer. I'm the group leader for this investigation and I'm Thea Jong. The other two group members for this investigation are Boon Pin and Shi Wei. For the remaining time in this video, we would like to discuss about the definition, technique used, and the working principle of the wireless power transfer. Besides that, we will also discuss about the advantages and the disadvantages of the near field and far field. Last but not least, we will also talk about the examples and the modifications of the wireless power transfer.
Do you guys know what is wireless power transfer? In fact, wireless power transfer is the transmission of electrical energy from an alternating current, or can be said as AC power source, to an electrical load without any physical connectors or wires. Please take note that in order to enable wireless power transfer, the power source must be AC current supply. You guys might be wondering why DC current cannot be used as power source during wireless power transfer. Don't worry guys, I will explain the reasons to you in the next few slides. At this moment, you guys just have to remember that in order to enable wireless power transfer, the power source must be alternating current. Now, let us talk about some history about wireless power transfer. Basically, wireless power transfer is a technology demonstrated by a Serbian scientist called Nikola Tesla. Nikola Tesla was the first person conducted research and proposed the concept of wireless power transfer in the late 19th century. He managed to light up a fluorescent lamp from a distance without any wires connecting the lamps to a generator. Next, we will talk about the technique used in wireless power transfer. Basically, wireless power transfer works based on the concept of electromagnetic induction. What is electromagnetic induction? Electromagnetic induction is the production of an electric current by a changing magnetic field. Now, let us discuss the concept of electromagnetic induction based on a simple experiment shown in this diagram. First, when you move the conductor wire here upside down between the magnet, you will find that there is a deflection of pointer in the galvanometer, which indicates the production of electric current in the circuit. Do you guys know why the electric current is produced? This is because when you move the conductor wire in the direction as shown in the diagram, there's a relative motion between the magnetic flux and conductor wire. The magnetic flux will be cut by the conductor wire. This causes an EMF, or can be said as electromotive force, to be induced across the conductor wire. Since the conductor wire is connected in a complete circuit, the electric current will be produced and flow through the circuit. That's all for the concept of electromagnetic induction. Now we will talk about the working principle of wireless power transfer. This slide clearly shows the simple setup of wireless power transfer. As you guys can see from the slide, wireless power transfer basically includes two main coils, which are a transmitter coil here and another one is a receiver coil here. During wireless power transfer, energy is transferred from the transmitter coil to the receiver coil through an oscillating magnetic field. Please take note, in order to enable wireless power transfer, oscillating magnetic field must be created. To accomplish this, the power source DC current has to be changed into high frequency AC by particularly designed electronics erected into the transmitter. As all we know that magnitude and direction of AC current varies continuously at a certain frequency. So, AC current supply able to create an oscillating magnetic field at transmitter coil. When the transmitter coil is powered by AC current, the magnetic flux of transmitter coil will be diverging and converging continuously due to the varying magnitude and direction of AC supply. Here are some main points that I mentioned in the previous slide. Maybe you guys can pause the video and have a look on it. But now, let us take some time to analyze the information shown in this graph here. From the graph, we know that the magnitude and direction of DC current remains constant all the times, while the magnitude and direction of AC current supply vary at a certain frequency. Please remember that in order to enable wireless power transfer, an oscillating magnetic field must be created so that the magnetic flux around transmitter coil can be cut by receiver coil and induce electric current in the circuit. Let's say, if we use DC current whose magnitude and direction remains constant all the times, an oscillating magnetic field will not be created. Therefore, there is no production of electric current in the circuit. This is the reason why DC current cannot be used as power source during wireless power transfer. Now, let us continue with the working principle of wireless power transfer. In the previous slide, I did mention that when the transmitter coil is powered by AC current, an oscillating magnetic field will be produced. The magnetic flux around transmitter coil will be diverging and converging continuously due to the varying magnitude and direction of AC current supply as shown in the diagram here. When the magnetic flux around the transmitter coil diverging and converging continuously, there is a relative motion between the magnetic flux and the receiver coil. So, the magnetic flux around the transmitter coil will be cut by the receiver coil here. This causes an electromotive force EMF to be induced across the receiver coil. If the receiver coil is connected to a complete circuit, alternating current will be induced and flows with same frequency as the electrical supply. Lastly, the electronics in the receiving device will convert the AC current back into DC current that becomes a working power. That's all for the whole working process of wireless power transfer.
The working principle of a wireless power transfer can be also described based on Faraday's law. This is because Faraday's law has stated the magnitude of the induced electromotive force EMF is directly proportional to the rate of change of magnetic flux linkage with the conductor. So, if we would like to increase the rate of change of magnetic flux linkage, we have to increase the induced electromotive force EMF. Therefore, there are few ways to increase the induced EMF. First of all, we can increase the number of coils of the receiver coil. Besides that, we can bring the transmitter coil closer to the receiver coil. Last but not least, we can increase the speed of the relative movement of the transmitter and the receiver to increase the induced EMF. So, what is near field? Near field is also known as a non-radiative technique. Power in a near field is transferred over short distances by magnetic field using inductive coupling between coils of wire, or by electric field using capacitive coupling between metal electrodes. So, the picture on the left is an example of inductive coupling. However, the picture on the right is an example of capacitive coupling. The advantage for the near field is non-radiative. This means that energy will stay within the short distance of the transmitter. Therefore, no power will be dissipated from the transmitter if there is no receiving device or absorbing material within the limited range. However, the disadvantage for the near field is the range of the near field is short. This means that the power that is transmitted will be decreased as the distance between the transmitter and the device increases. Hence, the technique for the near field cannot be used for long-range power transmission. Far field. Far field is also known as a radiative technique. Somehow, it is also called as a power beaming. Power in a far field is transferred by beams of electromagnetic radiation such as microwave and laser beam. So, why are microwave and laser beam used in far field technique? First of all, microwaves have long wavelength. This is so that it can transmit the power by diffracting through the obstacles. Next, laser beams are used in far field technique because they are monochromatic light. The monochromatic light can propagate through the narrow cross-sectional area for transmission over large distances. The advantages for far field techniques are far field can be used for long-range power transmission. This is because electromagnetic radiation can reflect, refract, and diffract the obstacles, and this increases the range of power transmission. Besides that, there will be no radio frequency interference to existing radio communication when laser radiation is used in far field technique. On the other hand, the disadvantages for the far field is part of the energy in a far field technique is radiative. This means that some energy will be dissipated and lost to the system during the transmission process. Next, laser radiation that is used in a far field technique is hazardous. This is because low power of laser radiation can blind a human and other animals, while high power of laser radiation can kill a person through a localized spot hitting when laser radiation is used without a proper safety mechanism.
Next, we would like to discuss the examples that uses the idea of wireless power transfer. One of the examples is the electric toothbrush. It is powered by a rechargeable battery and is charged through inductive charging when the brush is in contact with the charger stand. So, how does it actually works? First, the current from the wall outlet will flow through a coil inside the charger, which is this one. This will create a magnetic field. When the toothbrush is later in the charger, like you can see here, this magnetic field will induce a current on the secondary coil, which connects to the battery of the toothbrush. Then, this current will later recharge the battery of the electric toothbrush. Here, we have wireless phone charging. Wireless phone charging works by transferring energy from the charger to a receiver in the back of the phone through electromagnetic induction, but not through the wire. Its concept is quite similar to the electric toothbrush that we have discussed just now. First, the electric current will pass through the charger, and this will create an alternative electromagnetic field. A current will then induce in the receiver coil, and then the receiver coil will convert it back into electricity to be fed into the battery of the phone. One thing you need to take note is that those devices must have the appropriate hardware in them to support wireless phone charging, or else it will not work. Next, we have an example that uses the concept of far field of wireless power transfer, which is the space-based solar power. What is space-based solar power? Space-based solar power, SBSP, is actually the concept of collecting solar power in the outer space and distributing it to the Earth, as you guys can see through this figure. First, the satellites will be launched into the space, along with reflectors and microwave or laser power transmitter. Those reflectors will spread over the space, directing solar radiation onto the solar panel, like the wave here. The collecting satellite will then convert the solar energy into electrical energy, powering a microwave transmitter or laser emitter, and transmit this energy to a collector on the Earth's surface through the wave. And this one, which is this one. Now, we would like to discuss the modifications that may have been done in the recent years or in the future. As for the near-field charging devices, in terms of its physical distance, you may want to increase the physical distance of the electrical charge that can be transmitted. We also want to increase the electrical power that can be transferred through this way. And the most important thing is, in terms of its power loss, we would like to minimize it as to increase the efficiency of a device. Lastly, let us take a look at a few examples of future modifications. In the first figure, we hope that in the future, there will be a transmitting device inside home, which is probably being set up in the middle of the room, here like this one, that will transmit power to all the home appliances such as television, lamp, laptop, fridge, mobile phone, and so on. We hope that through this transmitting device, we can save our time by charging our home appliances at the same time. Next, we have the second figure. In this figure, it is shown that there will be power beam transmitter being set up on the roads, which is this one, as you can see here. This power beam transmitter will convert electricity into power beam, and then that beam will be transmitted to the power beam receiver on or inside the electrical vehicle. The power beam receiver will then convert the power beam into electrical power for the charging of battery inside the vehicle. Through this way, we can actually charge our electrical vehicle on the way we drive. Isn't that it actually become very convenient if this thing comes true?
That's the end of our video about wireless power transfer. Thanks for watching.